All right, let's go ahead and start our discussion on the integrated rate law for a second order reaction. So here what we're going to look at is we are going to start with A going on to form some products. And again, we'll have the change in the concentration of A over the change in time is going to be equal to K times then the concentration of A squared. So this tells us that it's second order with respect to A. So what we can do is we can integrate this expression. What we'll end up getting as our result is this equation down here. 1 over the concentration at time t is equal to K, which is your rate constant, times the time, plus 1 over the initial concentration. So remember that the units on your rate constant here, K, should be 1 over molarity per second, or molarity per minute, whatever it is, whatever your time unit is. So what we could do is we can actually start to look at this in a graph. We can plot the data of 1 over the concentration. So if you plot 1 over your concentration versus time, and you get a linear relationship, you could actually go through and calculate K by using the slope of your graph. Okay, but again, remember that here X is your time, just like it was for a first order reaction, but now Y is 1 over the concentration. So what we'll also see is how a second order diverges from a first order is if you're going to calculate the half-life of a second order reaction, it actually depends on what the initial concentration is. So your half-life will change depending on what your initial concentration is. For a first order reaction, we saw that it didn't matter what the initial concentration was. Your half-life was always the same. But for a second order, it is dependent on the initial concentration. So what we can do is we can plug in for our equation. So remember, we started with this 1 over concentration at times t is equal to K times t plus 1 over A naught. And here what we said is A naught's the initial concentration, but the concentration at time t for the half-life is going to be half of that initial concentration. That's the definition of half-life. The amount of time it takes for the reactant to reach 1/2 of its initial concentration. So we can plug in, and if we know the rate constant, we can go ahead and solve for that half-life. In this problem, I give you a set of data where it's time and then the concentration of NO2. And what I'm asking is, what order is this reaction? So in class, what we would have done is we would have made a graph. So we would have made 3 plots. We would have made a plot of concentration versus time. We would have made a plot of the natural log of the concentration versus time. And then a plot of 1 over the concentration versus time. And if you do this, and you can do this in your calculator or in a spreadsheet program, you should see that if we were looking at it for a 0th order reaction, so the concentration versus time, it looks like there's some sort of exponential relationship between the concentration and time. So since there is an exponential relationship, we can eliminate that this reaction is not 0th order. And then what we do is we would go ahead and plot the natural log of this concentration. So we go through and take the natural log, so the ln of all of these concentrations here, and plot that versus time. What we're going to see is that we have a fairly linear relationship. So we go ahead and run a linear regression, and we get our equation y equals mx plus b. But then we'd also display the r² value to look at the correlation of the data. And then just to make sure that we're being thorough and we're confirming that it's not second order, we would go ahead and plot 1 over the concentration versus time. So instead of taking the natural log down here, what we would do is we would take 1 divided by that concentration. What we're going to find is whenever we do plot this is that we have a pretty much perfectly linear set of data. So we have y equals mx plus b with an r² value of 1. So by making these three plots, what we've been able to do is we've been able to confirm that this is a second order reaction. All right, since this is a second order reaction, so we had our graph that would have looked something like this. And back here, sorry, I drew this line the wrong direction, should have a positive slope like that. So we'll have 1 over the concentration versus time. And what we can do is we can find K, because we know that K is going to be equal to the slope. So you'd run your linear regression, you'd find what M is, and in this case we would find that it is 0.541 per molarity per second. And you could get that by just finding the slope of this line. And you can do that with your calculator or in a spreadsheet. So the next question that was asked in this problem was, okay, so we figured out the second order, we figured out what the rate constant was, we double checked our units of our rate constant. So now we want to know what the concentration is of NO2 at time equals 20 minutes. So what we're going to do here is we're going to go ahead and start by converting our 20 minutes to seconds, because our initial data was in terms of seconds. So we'll have 60 seconds per 1 minute. We end up with 1.20 times 10 to the third seconds. And we're going to plug in to our equation for second order rate law. So we have 1 over a sub t is equal to kt, where k is your rate constant, times t plus 1 over your initial concentration. So here we're trying to solve for a sub t. So you'll plug it in. For k, the slope should have given you a value of 0.541 per molarity per second times your time. And then that will be plus 1 over the initial concentration. And the initial concentration is the concentration at time 0. So we're going to plug in this value right here, the 8 times 10 to the negative third. Okay, so what you'll need to do is you'll need to do some algebra here, and you need to make sure that you either take both sides to the negative 1. You just need to make sure that whenever you do end up solving for a sub t, that it's in the numerator. And what we should find is that the concentration of a sub t at this 1200 seconds is 1.29 times 10 to the negative third molar. So plug that in, make sure that it didn't make a silly algebra error. Make sure that you can solve for that as well. So the last part of the question is to go ahead and solve for the half-life with an initial concentration of 6 times 10 to the negative third. So what we're trying to do here is we want to show that the half-life is dependent on the initial concentration. So we're going to start with our equation for second order rate law up here again. Now our concentration at the half-life will be 1/2 of the initial concentration. So 1/2 of that is 3 times 10 to the negative third molar equals, and then we'll have our rate constant K, 0.541 per molar per second. We're solving for the half-life, and then here our initial concentration is 6.00 times 10 to the negative third molar. So going through and solving for t sub 1/2, so what you'll want to do for your order of operations is you want to plug this in your calculator, 1 divided by 3 times 10 to the negative third, and then subtract this over, so minus the quantity of 1 divided by 6 times 10 to the negative third, and then finally you'll divide both sides by the 0.541. And upon doing that, I believe you get 308 seconds. go ahead and double check that. And then try to make sure that you can do the next one on your own. Try to set that up. But I believe what you should get for your half-life for the second set of conditions, with an initial concentration of 3 times 10 to the negative third, you should get a half-life of 616 seconds. So the last type of reaction that we're going to talk about, I'm pretty sure that they would give you the equation for this if it showed up on an exam, is for a 0th order reaction. So we have A going on to form products, and our rate law is the change in concentration of A over the change in time. But then here, since it's to the 0th order, it's A to the 0th, which means A is 1, so the rate is equal to K. So upon integrating this, we obtain this expression here. Just like we did with first and second order reaction, we're going to look at what this would look like in a plot. So here, for a 0th order rate law, you would plot the concentration of A versus time. If you get a linear line, you could confirm that it is 0th order. And here, what we would find is the slope is equal to the negative of the rate constant. Okay, so your rate constant again is related to the slope. Just like a second order reaction, if you were trying to find the half-life for a 0th order reaction, you would have to plug in A sub 0, so your initial concentration, but then for A at some time t, you would plug in half of the initial concentration. Alright, so that wraps up our talk on integrated rate laws. So next time we will talk about reaction mechanisms. And please note, do smash that like button.